Hind student. My name is Pardeep and I am working as an assistant professor in IT department in Ajay Kumar Garg Engineering College, Ghaziabad. Today we will discuss the subject Theory of Automata and Formal Languages, and subject code is KCS 402. Okay, TAFL means Theory of Automata and Formal Languages. Okay. So today we will discuss the introduction of theory of automata and formal languages. It means what we will study in theory of automata and formal languages. Okay, with which TAFL deals. Okay. Now let's see the definition of TOC, or you can say TOC stands for theory of computation. Okay. TOC stands for theory of computation. Theory of computation. Okay. All these are same thing. Theory of automata, theory of computation, theory of automata and formal languages. All these are synonyms of the same subject. Okay. So in theoretical computer science and mathematics, the theory of computation is the branch, okay, is the branch that how efficiently problems can be solved, okay, and a model of computation solved on a model of computation using an algorithm. Okay, so basically it deals with how efficiently we can solve the problem, okay, and make an abstract computational model using some algorithm. Okay, and TOC is the bottom computer science, means it is the base of computer science. It is the base of computer science. Okay, there is one scientist during World War II, that is Alan Turing, who is known as the father of computer science. Okay, Alan Turing originate the term theory of computation. Okay, now in simple words, TOC deals with how to do fast computation, okay, and what computation we can do. In theory of computation, we basically build some abstract model, and in this abstract model we deals that how fast computer can do some computation, and what are the problems, what are the possible problems that a computer can solve. Okay, so it deals the fastness of the computation and what computation can be performed by computer. Okay, so there are some basic questions, 3 basic questions. Okay, the first question is, if something is true, is it possible to prove that always that it is true? Okay, and the second question is, if something is false, is it possible to disprove that always? And if something has some solution, is it possible to solve it always? Okay, let's see. If something is true, okay, is it possible to prove that it is true always? This term is very important, always. Okay, always. If something is false, it is possible to disprove that it is false always. Okay, and if some problem has some solution, is it possible to solve it always? Okay, so there are the 3 basic question. From these basic question we derive that what are the capabilities of a computer, that at what extent, at what type of problem computer can solve. Okay, so the answer of above 3 questions is no, it is not possible always. Always it is not possible, sometime it may be possible, but always keyword is very important. Always it is not possible. So if something is true, it is not always possible to prove that. Similarly for false case and similarly for solution. Okay. Now the theory of computation is divided into three major branches. First branch is computational complexity theorem, second branch is computability theory, and the third branch is automata theory and formal languages, or you can say languages or formal languages. Okay, I am writing here formal languages. Okay, formal languages. So these are divided into three major branches. Okay, next see. Okay, it is divided into TOC. In short, we write it as TOC, theory of computation. It is divided into three major branches. These three branches are linked by the question. What is that question? That what are the fundamental capabilities and limitations of computer? Means what are the fundamental capabilities and limitations of computer? Means that what type of computations or what type of problems can be solved by computers and what type of problems cannot be solved by computer or can be solved by partially. That this question will tell the capability of the computer, and limitation means that some particular type of problem cannot be solved by computer. So this comes under the limitations. Okay, so all these three theory deals with this one question. Okay, so by this question all these three branches are linked. All the three branches are linked. Okay, so to study the TOC or theory of computation, computer scientists work with the mathematical abstractions of computer called as model of computation. What it means? Suppose there is some problem. Okay, and there is some algorithm or some solution to solve that problem. So we build some model. Okay, abstract model to solve that problem. Abstract model of computation. Before implementing actual computer, abstract model of computation. Okay, and then actual computer, actual digital computer. Okay, so TOC deals with this abstract model. Okay, TOC deals with this abstract model. Okay, so to study TOC, computer scientists work with mathematical abstraction of computers. So computer scientists work on this abstract model. Okay, computer scientists work on this abstract model. Okay, and if this model is successful, then it is easy to convert into actual digital computer. Okay, next, computational complexity theorem, that it classifies problem according to their degree of difficulty. Means complexity theory consider not only whether a problem is solvable or not, but it also tells that how difficult is problem to solve. Okay, so complexity theorem consider not only whether a problem can be solved at all on a computer, but also how efficiently the problem can be solved. Okay, So there are two major aspects of this computational complexity theorem. First is time complexity. It deals that how many steps does it take to perform a computation, and second is space complexity. It deals how much memory is required to perform that computation. Okay, time complexity deals with the number of steps to solve a particular problem, and space complexity deals with the memory. Okay. So complexity theorem examples are, suppose that sorting a problem, it is an easy problem, okay, and scheduling problem, it is an hard problem. Second example is writing a letter, it is an easy problem. It means that writing a letter, it takes less time complexity and less space complexity, and writing a book, it will take more time and space. Okay. Third example is easy layout of universal logic gate. Okay. So to draw the layout of universal logic gate, it takes less amount of time as well as less amount of memory, and to draw VLSI, very large scale integrated chips board, then it required more time and space. So fourth example is 270 plus 230. We can easily find out that it is 500. It is 500. Okay, and 100 factorial. It is not possible for me to solve that easily. Although it is possible to solve, but it is difficult. Okay, it takes more time. So computational complexity theorem deals with this how problem that how efficiently the problem can be solved, that how much time and space can be required to solve a particular problem. Next, the fundamental question of complexity theorem is what makes some problem computationally hard and others as easy. This is the fundamental of that. What is the thing that why writing a book is difficult and as compared to writing a letter. Okay, writing a letter is easy as compared to writing a book. Okay, next is the computability theory or recursion theory. Both are the same thing. Okay, that what can be computed, what can be computed. It classify problem as solvable problem or unsolvable problem. Okay, the computability theory deals primarily with the question of the extent to which a problem is solved on a computer. Okay, and the computability theory is closely related to the branch of mathematical logic known as recursion theory, which removes the restriction of studying only model of computation which are reducible to Turing machine. Okay, so which removes the restriction of studying only model of computation which are reducible to Turing machine. Okay, so okay, so this computability theory deals with that what are the problem which can be solvable and what are the problem which are unsolvable. Okay, next let's see the solvable problem. What are the solvable problem? That the problem which have some algorithm, they means for the problem for which algorithm exists to solve them, these problem are known as solvable problem. Okay, for which algorithm exists. Okay, and means which have algorithm, and for those problem which prove mathematically that there is no solution for the problem. Okay, suppose there are some problem and we can mathematically prove that there is no algorithm for that particular problem, that also comes into the category of solvable problem. Okay, so suppose the decidable problem. Okay, decidable problem, Decidable problem means which have algorithm and procedure, and it knows the approximate time to solve a problem. Okay. Next is the unsolvable problem. Okay. An unsolvable problem is one for which no algorithm can ever be written to find the solution, for which there is no algorithm. It is a temporary state. It is very important. At present state, till now there are some problem which are unsolvable. Okay. So it is in a temporary state. Maybe in future there may be some technology or some way we find some way to solve that problem, then that problem comes into the category of solvable problem. So that's why it is written as it is temporary state, because at this point of time, at present, neither we are able to solve problem nor in a position to say that problem cannot be solved. Means we completely not assured that currently this problem is unsolvable. Okay. And we are not in a state that we can surely say that this problem cannot be solved by any mean in future. So okay, so that's why it is a in temporary state. So unsolvable problem do not have algorithm, till now do not have algorithm. In future maybe they may have. So for example, counting of stars in the universe. At present situation, at present we cannot count the star exactly. Okay, maybe in future it may be possible. Okay, so currently it is unsolvable. Next is time travel. Okay, we can't able to solve this problem currently, but maybe in future it may be possible. Okay, maybe in future it may be possible. So at present, this counting of stars and time travel is unsolvable, but maybe in future maybe it is possible. That's why it is in temporary state. Until now they don't have any algorithm. At present they don't have algorithm. Okay, because at present we are neither able to solve problem or nor in the state to say that problem cannot be solved. Okay. Third is undecidable problem. Okay, undecidable problem is a subcategory of unsolvable problem. Okay, so suppose there is some unsolvable problem. Okay, there are lots of unsolvable problem. Okay, there are some set of unsolvable problem. So undecidable problem is a subcategory of unsolvable problem. So suppose this set is undecidable problem. Undecidable problem. This set is undecidable problem. This subset is undecidable problem. So let's see what do you mean by undecidable problem. Undecidable problem is one for which no algorithm can ever be written. For unsolvable problem also no algorithm. Okay, there is no algorithm, and for undecidable problem also there is no algorithm. For undecidable problem also there is no algorithm. But what is difference between unsolvable and undecidable? There is some minute difference, that unsolvable problem for which there is no algorithm, that is correct, can ever be written, that always gives a correct true and false decision for every input. Okay, so there is some problem. Okay, unsolvable or undecidable problem means these problems are gives the answer in the terms of yes or no. Okay, either they gives yes or no. Okay, so for every input okay, they will not gives the correct input. Okay, this problem will not give the correct input. Answer is not correct for every input. These problem need not be yes or no. Only these problems are yes or no. These problems require the answer in the terms of yes or no. For this problem also, for every input, answer is not correct. Okay, means there is no corresponding Turing machine or algorithm. Okay, there is no corresponding Turing machine. Okay, these problem have only procedure but no algorithm, and they don't know approximate time. This undecidable problem keep on running, and we don't know whether it will stop or not, or whether they will give the correct answer or not. So there is no time limit. Okay, for example, halting problem of Turing machine is one of the example of undecidable problem. Second is finiteness, emptiness, and membership problem of Turing machine also comes under the category of undecidable. So these problem are halting problem of Turing machine, whether Turing machine halt or not for a particular problem. So this comes undecidable. Next is the finiteness, whether a particular language is finite or infiniteness problem. Okay, whether emptiness problem or membership problem. Member yes or no, finiteness yes or no, emptiness yes or no. These types of problem are undecidable problem. Next is the automata theory and formal languages. Okay, so abstract computing machine that accept different formal languages. Okay, automata originated from the word automaton, which is closely related to automation. Automata theory study abstract mathematical machine and computational problem that can be solved using these machines. So basically it deals the abstract mathematical machines. These machines are known as automata, and automata basically comes from the Greek word automata, which means something that is doing something by itself. So automata theory is also closely related to the formal languages theory, and it deals with the definition and property of different type of computing machines. Okay. Next is the formal languages. A formal languages consist of words whose letters are taken from an alphabet and are well formed according to a specified set of rules. Set of rules here means grammar. Okay, grammar. Next, language theory is a branch of mathematics concerned with describing language as a set of operation over an alphabet. Next, it is closely linked with the automata theory, because automata are used to generate and recognize formal language. Automata is used to recognize the formal languages. So this formal language theory and automata both are related. Okay. Next see, automata theory is closely related to language theory. In this context, automata is used as a finite representation of formal languages that may be infinite. Thank you.